Right. Good morning. So today we will continue with a bit of revision on differentiation. Like I said, most of these things you should already be familiar with. It shouldn't be anything new. If you can't remember, you need to go and find your notes for Math 1 and go over them. All right, so continue with number 9. We have y is equal to a to the power of x plus b to the power of c x squared. And we have to find the derivative. So remember, everything we're doing so far just involves your standard derivatives. So here you have a to the power of x. X is your exponent. So the way we would differentiate this is similar to the way we differentiate e to the power of x. So it remains the same, and then we multiply that by ln of a. Okay, and then this one over here, what we can do is we can always split it up and then differentiate it. So using our laws of exponents. Okay, so we have y is equal to a to the power of x plus b to the power of c times b to the power of x squared. Okay, and then you differentiate each of them individually. Okay, so like I say, this one from your table of derivatives. Just a moment, let me see this. Let me see if I can try and get this back. I don't know what's happening now. Just give me a moment. Okay, I hope you can see it now. Let me know if you can see it.
Yes, ma'am, we can.
Okay, all right. Okay, so from here, what we now do is we just differentiate. Let's see. Okay, this a to the power of x, the derivative of that is just a to the power of x multiplied by ln of a. So we have y prime. Now I've started the derivative. Or before that, let's simplify further. Okay, now you see this one here is different from that one because this is a to the power of x, and then this exponent over here is x squared. But what we can do about this b to the power of x squared is b to the power of x squared, we can rewrite it. So something you need to remember is that if I have a to the power of b, I can always rewrite this as e to the power of something, and then working out e to the power of something, finding its derivative is very simple to do. So this is e to the power of ln of a to the power of b. That is from your laws of logarithms. So something you did in STEM and even last semester. So here, so it doesn't matter what my b is, I can always rewrite it like this. And we know from our laws of logarithms, this b can come down, and I can write it as e to the power of b times ln of a. Okay, so here I have b to the power of x squared. So if I have b to the power of x squared, and I want to rewrite this as e to the power of something, this is e to the power of ln of b to the power of x squared, and then the x squared will come down. So this is just e to the power of x squared times ln of b. And this is very easy to differentiate because we can use the chain rule to differentiate it. Okay, so this is not necessarily a standard derivative, but we expect you to use your laws of logarithms, simplify it, and then use a standard derivative. So differentiating it now, first let me rewrite it. We have y is equal to a to the power of x plus b to the power of c multiplied by e to the power of x squared ln of b. And even this, you can separate it if you like. Y is a to the power of x plus b to the power of c times e to the power of ln of b times e to the power of x squared. Okay, and e to the power of ln of b is just b. Okay, so here again, no, sorry, I'm not confusing. That's not the laws of logarithms. If I'm multiplying, then I should raise it to a power. I think from here we just differentiate. Okay, so y prime, this is a to the power of x, ln of a. And then here, this is a constant because it doesn't have x. So our derivative will be the constant multiplied by the derivative of this one. This is e to the power of something. The derivative of e to the power of something is first e to that power, and then you multiply by the derivative of this. The derivative of your exponent is just 2x ln of b. So multiply by 2x ln of b. Yeah, go ahead.
Are we doing number 9?
Yes.
Now, where is the E coming from? While in the original question, there's no E.
The following, this is where I got the E from. This part here in red, that is where I just explained where we got the E from. Okay, then from here, what we do is we try and write this in its simplest form or as neatly as possible. This is a to the power of x ln of a plus b to the power of c ln of b times 2x e to the power of x squared ln of b. And then this one, again, we can have this as b to the power of x squared. And then, so just writing it neater, x ln of a plus b squared ln of b, 2x, and we say that this is e to the power of ln of b to the power of x squared. From your laws of exponents, the x squared becomes an x from your laws of logarithms. So this becomes an exponent, and then e to the power of ln of something is just that something. So this is a to the power of x ln of a plus b to the power of c ln of b times 2x, and then we have b to the power of x squared. Then again here, this one and that one, their bases are the same. Everything is multiplying, so we can combine the exponents. So you have b to the power of x squared plus c. So ln of a plus ln of b times, maybe here putting brackets is best so that it doesn't look like it's ln of b times something. So this, it's by itself, 2x b to the power of c plus x squared. So the derivative is, yeah, this pretty much, and then everything I've done after that is just trying to make it look a little bit better. But what you need to remember is sometimes you will need to simplify your expression, and then after that can you then differentiate it as a standard derivative.
Yes.
Yeah,
Oh,
I can barely hear you. You're like very soft.
in the law of indices,
Yeah,
won't we only multiply the bases when they are adding?
you're still very soft. I can't hear you. Can you, I don't know, move closer to the mic? Maybe to your earphones. Sometimes it's better without earphones. Yeah,
I will just type it.
go ahead. Let me see. You still want to ask your question?
I will type it, miss.
Okay. All right, then we move on to number 11.
Uh, Hello.
Yeah,
And if I'm seeing right, I'm seeing c plus x squared. But in the textbook at the back, it doesn't say that.
what does it say?
It says a to the power of x ln a plus b to the power of c x squared times 2cx ln b.
2cx. How did we get 2cx?
So got 2cx.
Sorry, say again. It's just like you're saying 2 and c are multiplying. How did 2 and c multiply? I don't see how that is.
Chain rule.
Unless the only way maybe they got that is by not separating these two like I have done. Maybe that's how they did it. Let's say you have y is equal to a to the power of x, and thus b to the power of cx squared, and then you rewrite it the way I did. This is e to the power of ln of b cx squared. This is a to the power of x, e to the power of cx squared, ln of b, then the derivative, a to the power of x, ln of a, plus e to the power of cx squared, ln of b, multiplied by 2cx ln of b. And then this one over here, this is just b c x squared. Is that what they have in the book?
Yes, ma'am. But it seems like you are using a long method, ma'am. Why don't you just use the standard derivative of a to the power of fx? Which is a to the power of fx times f prime times ln a.
You can use that. There's nothing wrong with that. Okay, so as you can see, there are other ways to do it. I always say choose the method that you prefer. As long as what you're doing is correct, you will always get to the right answer. So the answers sometimes look different, but they are in fact the same. Okay, that was number 9. And then, let me just see this. Then we look at number 11. We have y is equal to ln of e to the power of 2x plus ln of 2x. So this one involves differentiation of logarithms. So again, what we do is y prime, the derivative of ln of something is 1 over, even before that, we can always simplify. So this is just 2x plus ln of 2x, because the 2x will come down. Then you're left with ln of e, which is 1. So this is it in its simplest form. And then now you differentiate. So we have y prime. This is 2 plus 1 over 2x. And then you multiply by the derivative of 2x, which is 2. So here we should have y prime. This is 2 plus 1 over x. And then number 13, we have y is equal to ln of the square root of x plus x. Then here again, finding the derivative, this is a logarithm. So we have y is equal to 1 over the square root of x plus x, and then you multiply by the derivative of square root of x plus x. So we put it in brackets to show that it's the entire derivative that is multiplying by this, not just the derivative of square root of x. So this is 1 over 2 square root of x plus 1. And then you can simplify that as far as possible, or write it so that it looks a little bit neater. So here I'll just write it like this as a single fraction, but I'm sure you can even combine these two, have a single fraction, and then divide by that, and it might look better, but I think this is sufficient. So that was number 13 on logarithmic differentiation. Number 14, you would do it in a similar way. It involves simplifying it first. You have a logarithm, so you bring the exponents down, simplify it as far as possible before you start differentiating. Same thing with number 15. 16 as well. You want to separate the logarithms. And then number 17, that one. Number 17, we have y is equal to sine of 2x. Just take note of that. Y is equal to sine of 2x plus the square root of cos x plus the cube root of tan 2x. Okay, so this one involves differentiation of logarithmic functions, and the way we differentiate them, standard derivatives. So we have y prime. This is, for the first one, the derivative of sine is cos. So you have cos of 2x, and then you multiply by the derivative of 2x, which is 2. Then the same thing with this one. On the outside, we have a square root. That means to the power of half. So the half will come down. At the top, the exponent will reduce by 1. So you have minus 1, and then you differentiate the inside. So this will be a half cos x to the power of minus a half. So again, important, notice that the inside did not change when I differentiated the outside. And then you multiply by the derivative of cos, which is minus sine. So we have minus sine x. And then the last one, the cube root. So you have a third tan of 2x to the power of minus 2 over 3. Then you multiply by the derivative of the inside. So on the inside you have tan. The derivative of tan is sec squared of 2x. And then you multiply by the derivative of 2x, which is equal to 2. Okay, then the only thing left is to now just write this in its simplest form, work out any things that you need to work out. So you have y prime. This is 2 cos 2x. Then this second term will be negative because of this negative sign. So you have minus sine x over 2 square root of cos x. And then here you have 2 over 3. Okay, I have 2 over 3 and sec squared 2x over the cube root of tan squared of 2x. So that's what we have for number 17. Okay, so here trigonometric differentiation as well as the chain rule. And for the third term, we had to use the chain rule twice. So make sure you use the chain rule correctly. Then number 19 also involves trigonometric.
Yes.
Yeah.
Could you go back not to number 17? Okay, thank you.
Okay, number 19, we have y is equal to cos the square root of x plus the square root of cot of x squared. So again, here we will be using the chain rule. We can't simplify it any further before we differentiate, so we just get straight into differentiation. The derivative, of course, is negative sine, so I have negative sine square root of x, and then you multiply by the derivative of square root of x, which is 1 over 2 square root of x. Then this one on the outside, I have square root or the power of half, so the half comes down at the top. I reduce the power by 1, so I should have half cot x squared to the power of minus a half, and then that you multiply by the derivative of cot. The derivative of cot is minus cosec squared. Okay, so it is minus cosec squared of x squared, and then multiply that by the derivative of x squared, which is 2x. And then you just write it nicely. You can see this half and the 2 will cancel. And yeah, that's it, that can cancel. So we have y prime this is negative sine square root of x divided by 2 square root of x. That's combining these as a single fraction. And then this one in the numerator, I will have negative cosec squared x squared times x. So remember, this half and the 2 cancel. So I have negative x cosec squared x squared. That's in the numerator. And then in the denominator, I have the square root of cot x squared. Okay, that's number 19. Number 20, that one is fairly simple. You just use the quotient rule. So again, remember everything you did in Math 1, you need to take it with you because you will be using it at one point or another. And look at number 21. Y is equal to e to the power of cos x plus ln of sec of x over 2. So here, this is logarithmic, exponential, trigonometric, but we know how to differentiate each of these. So for the first one, the derivative of e to the power of cos x, e to the power of cos x remains as it is. Then you multiply by the derivative of cos x, which is minus sine x. So we have y prime. This is e to the power of cos x multiplied by negative sine x, which is the derivative of cos x. Then the second term, this is ln. The derivative of ln is 1 over sec squared. Remember, 1 over sec squared is just cos. Sorry, not 1 over sec squared. 1 over sec is just cos. So this is 1 over sec x over 2. And then you multiply by the derivative of sec. The derivative of sec is sec tan. So you have times. So here I'm multiplying sec x over 2 tan x over 2. And then you multiply again by the derivative of x over 2, which is a half. Okay, so then simplify as far as possible. So we have our y prime. This is negative. You write the e first. Negative e to the power of cos x sine of x. And remember that, okay, here I have 1 over sec, and this is sec, so those two will cancel each other out. So I'll be left with half tan x over 2. So this is plus, yeah.
Where is the 1 over 2 coming from?
The derivative of x over 2.
Okay.
Okay, so that is your answer. Let me just see. Okay, yeah, so that is your answer. Negative e cos x times sine x plus a half tan x over 2. Okay, number 22, there you must just use the product rule. 23 is pretty much the same as this one that we did. This is logarithmic exponential. Wherever it's possible, try and simplify your expressions first. Like you have ln of sine squared x, the 2 can come down, and then you differentiate it. That might be easier to work with. Same thing with number 20. Yeah.
Going back to number 19.
Yeah.
I'm a little bit confusing in the original equation. Is that power of 2 for x only or for the whole function?
No, for x only. If it was for the whole function, the 2 would be here.
Okay, ma'am. Thank you.
All right. Okay, then let's look at number 26. We have y is equal to x squared times 2 to the power of x. So here we are going to use the product rule because you have two functions of x multiplying. So we say that y prime, this is the derivative of the first one, which is 2x, and then you multiply that by the second one exactly the way it is. And then you write down the first one as it is, and then multiply that by the derivative of the second term. So this is the product rule, a rule that we went over yesterday and that you should know. Okay, and then can simplify this as far as possible, though there isn't very much you can do. You can factor out 2 to the power of x. And just see 2 to the power of x, sorry, 2x, 2 to the power of x. Okay, and here you could combine this 2 and this 2 to the power of x, but I don't know if that makes it look any better.
But Miss,
Yeah.
Can you be able to factor out the 2x, 2 to the power of x?
Yeah, I said you can do that.
Okay.
Yeah, but it doesn't really make it look that much better. So I think even leaving it like that is sufficient. Then number 27, we have y is equal to log base 4 of x. Here they're multiplying. Let me just check what I wrote here. Okay, yeah, they're multiplying. So times 10, or the 10 cubed of 3x. So again, here we have to use the product rule. So this one here, you can always rewrite it as ln. I prefer to rewrite it. You can use the standard derivative, how you do it, but in the end, our answers will be exactly the same. So here, this is ln of x over ln of 4 multiplied by 10 cubed of 3x. And now we use our product rule. So remember, this is my first function. That is my second function. So y prime, this is the derivative of this is just 1 over x ln of 4. And then the second function, I write it down exactly as it is. So this is 10 cubed of 3x. And then the first function, I write it down exactly the way it is. So this is ln of x over ln of 4. And then I multiply by the derivative of this. So this is something to the power of 3. The 3 must come down. I have 10 squared of 3x. Then I differentiate 10. The derivative of 10 is sec squared. So I have sec squared of 3x. And then you multiply by the derivative of 3x, which is 3. Okay, so here you must use the chain rule 3 times. And then simplify as far as possible. Let's see. So our y prime, this is 10 cubed of 3x over x ln of 4. That's for the first term. Write it as a single fraction. Then for this one, we have 3 times 3. That gives us 9. 10 sec and ln of x will be multiplying. So this is 9 10 squared of 3x sec squared of 3x ln of x. This is all divided by ln of 4. Okay, so just writing it so it looks a little bit better. Sec squared is 1 over cos. Okay, there isn't anything that can cancel, so we can leave it like that. Then number 28. we have y is equal to tan of e to the power of cos of 2x. So here we just have to use the chain rule. So on the outside we have tan, so the derivative of tan is sec squared.
Miss,
Yeah.
can we quickly just go back to the number 27? I just want to check something. Okay, so
So we have sec squared of e to the, please mute your mic. Sec squared of e to the power of cos 2x, and then you multiply by the derivative of e to the power of cos 2x, which is e to the power of cos 2x multiplied by the derivative of cos 2x, which is minus sine 2x, and then you multiply by the derivative of 2x, which is 2. Okay, and then we simplify this as far as possible. So our y prime, this is negative 2 e to the power of cos 2x sine of 2x sec squared of e to the power of cos 2x. So that is how we would write that one. Okay. Then the other questions that I didn't do in that section of that exercise, you should try them and do them. They're all pretty similar, just involving standard derivatives, nothing too complicated. Then look at number 31. Let me just read what number 31 says. So number 31 says, prove that the following differential equations are satisfied by the given y values. So our last chapter for this course is differential equations. So we will actually be solving equations like this, like 31, 32, and 33, where you have to work out what that y value is. Well, oh, this is second order, maybe not, but we will be dealing with differential equations. Now this one where we have to prove that that it satisfies it, all we have to do is substitute it into the equation and show that when we substitute it, it satisfies the equation. So we're given that y is equal to a to the power of e to the power of minus x plus b to the power of e to the power of minus 2x. And what we are saying is that it satisfies the equation. I'm going to write it in short. The equation is y double prime plus 3y plus 3y prime plus 2y is equal to 0. So what that means is when I find the second derivative, I'll substitute it there. First derivative substituted there, and y as it is substituted there. And when I add everything, my answer should be equal to 0. So we need to find the first and second derivative. So y prime, differentiate this. This is negative a e to the power of minus x. And the derivative of this is negative 2b e to the power of 2x. Okay, we also need the second derivative so that we can substitute it over there. So we say y double prime. This is just the derivative of the first derivative. So we will have a e to the power of minus x, and then 4b e to the power of minus 2x. So now I have everything I need. I have the second derivative, I have the first derivative, y is given to me in the question. So we just substitute them in this equation and then show that the answer will be equal to 0. So doing that, so we say substituting. Into the equation, we get y double prime. We have a e to the power of minus x plus 4b e to the power of minus 2x. So the only reason I'm putting them in brackets is to like separate them so you can see, oh, this first bracket is y double prime. It doesn't have to be in brackets here. And then the next one, we have 3 multiplied by y prime, which is minus a e to the power of minus x, then minus 2b e to the power of minus 2x. So this one has to be in brackets because it's multiplying by the 3. This one doesn't have to be, but the brackets don't change anything. And then we add 2y. 2, so y is a to the power of e to the power of minus x plus b e to the power of minus 2x. So here I don't just automatically put equal to 0. I have to work this out and show that the answer is in fact equal to 0. That is how you check that it satisfies the equation. So now rewriting this without brackets and multiplying this in, we will have a e to the power of minus x, 4b e to the power of minus 2x, and then minus 3a e to the power of minus x, minus 6b e to the power of minus 2x, plus 2a e to the power of minus x, plus 2b e to the power of minus 2x. And then we collect our like terms. So you can see this e to the power of minus x. There's another one here, e to the power of minus x. And this one over here, which is e to the power of minus x. So I have a minus 3a, which is minus 2a, minus 2a plus 2a is 0 times e to the power of minus x. And then this one's here, the ones that have e to the power of minus 2x. Let's see that one. So I have 4b minus 6b, that's minus 2b plus 2b. This is all equal to 0. So therefore, y satisfies the equation.
Well,
Yeah.
we have such questions in the first test.
Yes, why not?
Maybe we didn't cover that topic yet.
What did I do that you have not covered?
The part of the differential equation.
All I did was differentiate. Was there any differentiation technique that I used that you don't know?
No, ma'am.
Okay, and then after that I substituted. I hope you know how to substitute. So there's no reason why you should not get a question like this in the test.
Miss,
Okay, yeah.
do we have to check also in the question paper?
What do you mean, do you have to check in the question paper?
Like to prove that it satisfies the equation.
This question said that's what you must do. So that is what you're supposed to do.
Well, I thought we are only ending at the differentiation part.
No, the question said you must prove it or show that it satisfies it. So you must show it. Okay, so number 32, you'll do it in exactly the same way. It's just differentiation. So questions like this are meant to open your mind so you see, oh, this is what we are going to do later on when we do differential equations. Yeah, but number 32, you do it in the same way. Number 33, you would also do it in the same way. You just differentiate and then substitute and show that the answer is equal to what you have on the other side. And then we have logarithmic differentiation, which was another technique that we did last semester. And I'll keep saying this, you don't remember any of these things, you need to go back and find your notes and go over that. So with logarithmic differentiation, usually we use this when what we have maybe on one side or both sides, you have fractions, for example, you have exponents that are rather tricky to differentiate, so introducing a logarithm makes them easier to differentiate. So let's look at the first example that we have. We have y is equal to 1 plus x, 1 plus 2x over 1 minus x and 1 minus 2x. So this one you can easily, easily differentiate it using the quotient and the product rule, or you could multiply out the brackets and then just use the quotient rule, but that would take quite a bit of time. So a better way to do this might be to introduce logarithms on both sides. So you take ln on both sides. So we have ln of y. This is ln of this entire fraction. Let me just copy it. Okay, so you take ln of the entire fraction, and we know how the laws of logarithms work. If you have a product, you can write that as a sum of logarithms. You have a quotient, you write that as a difference of logarithms. So what I have, in fact, is ln of y, ln of 1 plus x, plus ln of 1 plus 2x, minus ln of 1 minus x, minus ln of 1 minus 2x. So this is what we have, and differentiating this is certainly less time consuming than differentiating this using the product and quotient rule. So to differentiate ln of y, remember y is a function of x, so ln of y, its derivative is 1 over y, and then you multiply by the derivative of y, which is y prime. And then the rest, we differentiate them normally. Ln of this is 1 over 1 plus x, and then you multiply by the derivative of 1 plus x, which is 1. So since I'm multiplying by 1, I don't need to write it. You can show it so that in future when you're working it out, you take note of it, but here I don't need to write it. Same thing with this one. The derivative is 1 over 1 plus 2x, and the derivative of 1 plus 2x is 2. So in the numerator, we'll put a 2 over there. And then here, this is minus 1 over 1 minus x. And then the derivative of 1 minus x is minus 1. So you have minus 1 multiplying with this minus, and then it will change to positive. And then over here, you have negative 1 over 1 minus 2x. Then you multiply by the derivative of 1 minus 2x. The derivative of 1 minus 2x is negative 2. So negative 2 will multiply with this negative over here. It will become positive. And then in the numerator, we will have 2. So remember what we were trying to work out. We want to find y prime. So you can multiply by y throughout. So we have that y prime. This is y times 1 over 1 plus x plus 2 over 1 plus 2x plus 1 over 1 minus x, 2 over 1 minus 2x. Okay, and sometimes when your y isn't a very complicated or long expression, you can rewrite what y is. So what I mean by that, see if I have space, put it here. Write it like that. And this one here. Okay, then you put your brackets like that. So sometimes it's good enough you just leave it like that when your y is some very long expression. Otherwise, you can always substitute it back like that. Okay, so we'll continue from here tomorrow. So go and look at those questions on logarithmic differentiation, and hopefully we'll also finish with implicit differentiation tomorrow, and then Friday maybe we can start on arc-trig functions. Okay, so I'll stop here for today and I will see you guys tomorrow.
Miss, but Miss,
Yeah.